Hey guys, I'm just going to do a really quick video tutorial on bits of security, hopefully get you ready for the exam. So the first question you might ask is, why do we use bits of security? Well, let's start off with an example. Say, for example, you had a password field that has maybe 1,000 unique passwords. One way of describing how many possibility passwords there are is to just say there are 1,000 unique permutations. Perfectly fine. But when it comes to security, often we're not dealing with 1,000 unique possible passwords. We're often dealing with a lot more. You've probably heard of AES. It's the best standard we have for encryption. You've probably seen AES 128. Well, what that's talking about is actually bits of security. So back to the 1,000 example, let's say we wanted to calculate how many bits of security that has. Well, what you do, just really quickly, is you find the nearest power of 2 number. So, 2, 4, 8, 16, 32, 64, 128, etc., etc. The closest number for this one is 1024. What you do is you convert that back into powers of 2. So 2 to the 10 is actually equal to 1024. And the bits of security is just this exponent number here. It's the 10. That's literally bits of security. So the challenge is always to find out how many unique combinations you have, find the nearest power of 2 number, put it in a power of 2, and then take this exponent. But the reason we do that is it could be easy to say 1,000, but what happens when you have AES 128? Well, AES 128 is talking about the length of the key. It's a key in ones and zeros. So there's literally, this is how many options there are for AES 128-bit. So you can see there's a ton of options there. And when we want to compare maybe, say, this 10-bit password, 10-bit, versus AES 128, it's a lot easier to see that 128 versus 10, that 128 is a lot more secure. And we'll talk about at the end, hopefully, how we know 128 is a pretty good, reasonable number. But let me go to an example. So let's say I do have a password. Let's say my password is 1, 2, 3, 4, 5. Let's say it's 8. Can't count. 8 characters. And my users, I'm going to allow them to use passwords A to Z, capitals, also A to Z, lowercase, and then 0 to 9. So that means with this password, how many options are there? For the first letter, they can choose one of 25. They can also use a lowercase. They're going to use one of these digits. So there's 10 options there. Add them all together, we get 62. So you've got 62 options here. And for the second category, second character, they can do the same, 62. So you can see, I'll just write it all out. 62 times 62 times 62. What we have, the total number of options for this password, unique permutations of unique passwords we could have, is 62 to the power of 1, 2, 3, 4, 5, 6, 7, 8. Well, it's 62 to the power of 8. Now, there's a really quick way of calculating the bits of security. It does involve a bit of maths. What I'm going to do is I'm just going to write that down, and if you like maths, you can do it this method. I'll explain the kind of more logical method you can do in your head. But if you just really quickly wanted to calculate bits of security, you get the total number of permutations, and you just solve this question here. What is the log base 2 of the total number of permutations? So whatever that is, that will be your bits of security number. But let's do this a little more logically. So I'll just take this and I'll get rid of this hideous maths and we'll just throw it away over here somewhere. Cool. So let's try and solve this using our head and using logic. The best way to solve bits of security is first calculate the number of unique permutations and then find the nearest power of 2 number and then just take the exponent. So this isn't a power of 2 number at the moment, this 62 value over here. So let's convert it to a power of 2 number. I'm noticing 62 is very close to 64. So in this case, it's totally fine to just round it to the nearest power of 2 number. So I'm going to do that. I'm just going to say 62 to the power of 8 is approximately equal to 64 to the power of 8. And that's a pretty reasonable guess and assumption. And now I know that 64, well, 64, I know that's a power of 2 number. I'm just going to write down the bottom all the power of 2 numbers. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, oh gosh, 2 to the 5 is 32, 2 to the 6 is 64. Awesome. And if I didn't know that, I could just double them, start with 1 and double it. So 2, 3, 4, 5, 6, 7. So yeah, it's I know that 64 can also be written as 2 to the 6. So I'm just going to write that 2 to the 6 and just replace that 64 there. And then it's still the power of 8. Now the way log laws work is you can just, if it's something to the power inside the brackets and there's a power outside the brackets, you can just multiply these numbers. So golly, what is 6 times 8? That's 48, isn't it? So the total number here is 48. So see what I've done there? I've taken the full number of permutations here, and then I've converted it to the nearest power of 2 number, which is 64. I've actually converted it to the base of power of 2. And then the bits of security value is this value here. So if I had a password which had, a letter or a number, eight of them, then what we're saying is that password has 48 bits of security. If you wanted to do it another way, you could do it this way. You could say that 64 is close to 62 rather is close to 64 times 64 times 64 64, and 64 we know from before can be represented as 2 to the 6 times 2 to the 6 times 2 to the 6 times 2 to the 6, etc., etc., etc. So I'll do it in full. 2 to the 6 times 2 to the 6 times 2 to the 6 times 2 to the 6. And we just add the way log laws work, or powers of 2, I should say, is we just add these numbers here. So it's 6 plus 6 is 12, plus another 12 is 24, and plus another 6, 24, 30, 36, 42, and then 48. So I just add them all up here, and I'll go, that's 2 to the 48, which we saw from before. That was the answer there from before. So that's essentially how you do bits of security. Now, often when you calculate bits of security, let's just scroll up a bit, have a clean page. We now our 1, 2, 3, 4, 5, 6, 7, 8 password. 8-character password has, 48 bits of security. Often you'll be asked, how is that reasonable? And in order to know if that's reasonable, what you have to do, I just dropped my face down the bottom. In order to calculate if that's reasonable, you have to guess how long it would take to brute force it. So often the question will say, calculate how many bits of security it has, and then calculate how long it would take to brute force it, and justify any assumptions you make. Well, this is how you'd make those assumptions. For example, my computer in front of me is a 1 gigahertz frequency, I think it is, frequency machine. And what that means is it can do 1 billion clock cycles per second. Now, it requires a bit of a knowledge of the lower computers, but not really. We can just make assumptions, like the computer does really little instructions, like it adds something or loads a number from somewhere else, and it can do 1 billion of those calculations per second if it's a gigahertz machine. Let's be really optimistic here. Let's assume the best case scenario. Let's assume that my cracking attempt is super efficient, right? And that I can literally do, well, this can do 1 billion instructions per second. This is totally wrong and totally optimistic, but I'm just going to assume they can do 1 billion password guesses per second. Very optimistic, but let's just assume that. So what I'd need to do is I'd need to convert this to bits of 2. And these questions confuse people all the time, and it's really not that hard. I want you to think of this analogy here. Let's say there are 1,000 pizzas. Oh, I can't spell. And I, Adam, a very hungry person, can eat 10 pizzas an hour. I'm pretty hungry. So if you wanted to, and I can eat Adam, I'll just put me, 10 pizzas an hour. If I wanted to calculate how long it takes me to eat 1,000 pizzas? Well, that's easy. I just take the 1,000 pizzas and I put it over the 10 pizzas. So I say like 1,000 pizzas divided by 10 pizzas per hour. Well, and we just cancel, right? We go cancel pizzas, and we get what we get is we get 100 over 1 over hours, which because that's on the bottom, it just becomes 100 hours. So this is exactly like the security questions. For example, it's how many you have and how quickly you can do them. How many you have, how quickly you can do them. So in the previous example, we said we had 48-bit password. What that really means is it means there are this many possible password combinations. It means 2 to the 48 possible password combinations. And what we set up here is we said I can do a billion password guesses per second. So how many seconds is it going to take me to guess them all? Well, we just do the same thing we did here with the pizza. We said 1,000 pizzas, so there are 2 to the 48 passwords. And how many can I do per second? Well, I can do a billion. So I'm just going to put a billion down here. If you don't know, a billion can be written as 1 times 10 to the 10 to the 10 to the 9. And then we can just figure out the answer here. And that is how many? Let me guesses. So I'm going to write this. Write the units. Passwords per second. So we can just calculate what that result is, and that will tell me how many seconds it'll take me to guess every single password. So before I do that, I'm just going to convert it to an actual number. And so this is in 2 to the 48. I'm just going to convert a billion to a power of 2 number. So what's the closest power of 2 number to a billion? Well, there's a little shortcut. 2 to the 10 is 1,024. And 2 to the 20 is approximately equal to 1 million. And 2 to the 30 is approximately equal to 1 billion. So that's a great number to remember. 2 to the 30 is approximately 1 billion. If you wanted to know what half a billion was, a billion, well, you just take 2 to the 30 and you divide it by 2. And let me get rid of this. I'll write that again. 2 to the 30. What's half of a billion in half a billion in power of 2 number? Well, you just take 2 to the 30 divided by 2 to the 1, and the way the log laws work is you just deduct, you take away 1 from 30, so it just becomes 2 to the 29. So there's a really nice shortcut for you there. Yeah, so anyway, distracted. So we're trying to figure out how many passwords I can crack per second. So we take all the number of passwords we have to crack, which is, like the number of pizzas. And then we divide it by how many pizzas I can eat per second, or how many passwords I can crash per second. We know that's 10 to the 9, but we also know that 1 billion can also be represented as approximately equal to 2 to the 30. So we'll do that here. So the number of seconds it'll take me to complete, well, I just solved this equation here, and we know with log laws we can just do it this way. 48 minus 30 is 2 to the, 18? So this is how many seconds it'll take me to brute force them every single password. But what you'll notice that if I asked you, it won't actually take me all this amount of seconds to find a random password. Because often when you're trying to find one single password, well, on average, you're going to find it halfway through. And let me give you an example of that. If I asked you to pick a number do it right now, pick a number from 1 to 10. And I'm just going to list them all here. 4, 5, 6, 7, 8, 9, 10. So pick a number in your head. You got it in there? All right, in your head. Was the number 2? Probably not. Was the number 4? Probably not. What about 5? No. What about 1? No. Was it 1? No. Was it 3? What about 8? 9? What about 10? Was your number 7? No, cross that out. What about 6? So what you'll find in that exercise that sometimes when you pick a number, I'll guess it the first time round. And sometimes I'll guess it on the last time round. But on average, I'm going to guess it halfway through. So it's going to take me 5 guesses before I guess it, statistically, on average. If we looked at 10 people who did it, it would have taken me on average about five guesses to get it. So likewise, if I'm trying to guess, if I'm trying to brute force my password up here, although to brute force every single password, it's going to take 2 to the 18 seconds. On average, it's just going to take half that time. So the way you do that is just go 2 to the 18 divided by 2, and 2 can also be written as 2 to the 1. So it just becomes 2 to the 17 seconds on average. So to know whether you need to, how long it will take, whether you need to figure out the average or the maximum time, you just look at the question, and the question will say, on average, how long will it take to brute force a password? Or it'll say, what's the worst case scenario to brute force a password? So that's quickly how you do bits of security. Let me quickly talk about what's an appropriate amount of bits of security. If somebody comes to you and says, I have a new password scheme, is it secure? Well, the magic number that we have in our heads that we think is a pretty secure number is 128. That's like our gold standard. But I hear you being skeptical, and good on you for being skeptical. Why 128? Well, we do a little calculation, and it's just an example, like how long will it take for somebody to brute force or something with 128 options? So how many options does somebody have to brute force if there's a 128-bit password? What that means is that there are this many possible passwords, 2 to the 128. So let's just look what that is. Just Google it here. 2 to the 128. It's a massive number. It's 3 times 10 to the 38. So to compare that, I didn't write 38, did I? To compare that, we want to compare it against some other numbers we know. So this is a really contrived example, but let's do it. Let's calculate the number of seconds since the beginning of the universe. So we'll type in number of seconds in a year. Okay, so it's that many seconds. And then number of years since the Big Bang. Oh, where is that number? Nothing tells me. Okay, hang on. How old is the universe? Maybe Google doesn't believe in the Big Bang. Okay, 13.8. You can probably see it just there. 13.8 billion years. So what I'm going to do is I'm just going to multiply those numbers to find out how many seconds there have been since the beginning of the universe. So 13.8 e to the 9 gives me 13.8 billion years. I'm just going to go times the number of seconds in a year. Let's figure out how many seconds there are since the beginning of the universe. So there we go. So the number of seconds since Big Bang is 4.3 times 10 to the 17. So you can see, based on that quick calculation we did there, that when a password has 128 bits of security, it has this many unique passwords. And even if we tried typing in a single password on the computer every second since the beginning of the Big Bang, we wouldn't even be halfway through. Like, this is how many seconds there have been since the beginning of the Big Bang. There haven't been as many seconds since the beginning of the universe as there are unique passwords when a password has 128 bits of security. So that's why we consider 128 to be a pretty secure password. I think that covers everything. If you have any questions, let me know. I might do another bits of security example in a Merkle puzzle video. Hope that makes sense, and good luck with your exam.